This is the beginning of Chapter 6 for Physics 30. Chapter 6 is all about gravitational fields, so we're going to start with Lesson 1, which is about universal gravitation. Newton's law of universal gravitation states that the gravitational force between two masses is proportional to each of the masses and inversely proportional to the square of their separation. What that means when we say that something is proportional to the two masses, essentially it means that we're multiplying them together, which you can see here in the equation underneath, that mass 1 and mass 2 are being multiplied together. And inversely proportional just means we're dividing by something to the square of their separation. So we're squaring the amount of distance between the two objects. This is what we know as Newton's law of universal gravitation, where the force is equal to g. Now, we don't want to get this g confused with the force of gravity, which we know to be 9.8 meters per second squared. This is a gravitational constant, which is listed down underneath. It's 6.67 times 10 to the negative 11, so a very small number. And that's in the unit Newton multiplied by meters squared over kilograms squared. So this universal gravitation says that the force will be equal to the gravitational constant listed below, multiplied by mass 1, which is the mass of the object being orbited, multiplied by the mass 2, which is the mass of the object doing the orbiting, and then r is the radius of their distance. So that would be calculated, if we're thinking planet-wise, from the center of one planet to the center of the other planet. If you're talking about objects that are directly on the surface of a planet, so maybe an example is we have someone standing on the surface of Earth, then mass 1 would be the mass of the Earth, mass 2 would be the mass of the person, and r squared would be from the center of Earth to the center of the person, or in other words, in that case, r would really just be the radius of the Earth. So this tells us that any two bodies attract each other gravitationally, and this is true for all objects, not just planets and not just ones that spin. Anything that has a mass will have some gravitational pull from it. Henry Cavendish is one of the first thinkers who really demonstrated this through his Cavendish experiment, which is pictured in this diagram, where he built this large wooden box, and inside of it he placed an apparatus that suspended two large spheres as well as two small spheres, which you can see here and here. And the two small spheres were attached to this rod. The rod hung from a wire, and the idea being that the small spheres should be attracted to the large spheres, which would then make this rod turn, which would then in turn twist this wire. Once the torque in the wire was sufficient to overcome the gravitational pull of the small spheres, the torque would start to unwind, the spheres would start to move away from the larger spheres until again they passed the point of equilibrium and gravitation pulled it back again. So in that case, the small spheres should oscillate slightly between the big spheres. They should move back and forth a little bit. So there's a video here you can watch that explains that a bit more in depth that will be available in ETB. This can also be replicated with the device you see on the side here, where large spheres attract small masses that are inside the canister, and deflection can be accurately measured. An example. What is the force of attraction between an 80-kilogram boy and a 50-kilogram girl when they are 1 meter apart? Mass 1 is 80 kilograms and mass 2 is 50 kilograms, and the radius of their separation is 1 meter. We know that we're using this equation where the force will be equal to the gravitational constant multiplied by both masses and then divided by their radius squared. So gravitational constant 6.67 times 10 to the negative 11, multiply the 80 and the 50 over 1 squared, And we find that the force of attraction should be 2.7 multiplied by 10 to the negative 7, and that's again measured in newtons. Looking at gravitational field strength, or in other words, acceleration. The acceleration, or the force of gravity, should be equal to gm1m2 over r squared. Now we know that force is equal to mass times acceleration, so on the left-hand side we can replace Fg with mass times the acceleration due to gravity. Here we've represented that with a lowercase g. And then on the right-hand side we have the gravitational constant multiplied by the mass of a planet and the mass of an object orbiting said planet divided by the radius squared. Now, because we have the mass of the object on both sides, we can simply cancel those out, leaving us with this equation. And so that would tell us that the acceleration, notice here that lowercase g in this equation and lowercase a in this equation, or lowercase alpha, these two represent the exact same thing. It's saying the acceleration due to gravity will be equal to a gravitational constant multiplied by the mass of an object divided by its radius squared. Using that the acceleration due to gravity should be gm1 over r squared, we can calculate what is the gravitational field strength on Earth. The radius of Earth is 6,371 kilometers, and the mass of Earth is 5.97219 times 10 to the 24th kilograms. Now, when you plug this in, it's important to convert the radius of Earth from kilometers into meters. Calculating this all out, we get 9.8 meters per second squared, or 9.8 newtons per kilogram. So we've been using the 9.8 for a while, just assuming that it's true and correct, and this is where it actually comes from. It comes from multiplying the mass of Earth by the gravitational constant, and then dividing by the Earth's radius squared. And you can do this for any planet. So we can also do this for the strength of gravity on the moon. The mass of the moon is listed underneath, as is the radius. So using the same equation, we can plug in the gravitational constant, the mass of the moon, and the radius of the moon squared. Calculating it all out, we should arrive that the acceleration of gravity on the moon would be 1.6 meters per second squared, or 1.6 newtons per kilogram. How fast does the Earth move in orbit around the Sun? Two things are listed for you here, the mass of the Sun as well as its radius. Or sorry, that's not the not the radius of the Sun. It's the orbital radius of the Earth around the Sun. So in order for something to orbit the Sun, the force of its acceleration would need to be equal to the gravitational force. So we can say that mv squared over r has to be equal to gm1 m2 over r squared. You should hopefully recognize this mv squared over r as the acceleration, the centripetal acceleration of an object moving in a circle. So this would be the centrifugal force of Earth as it orbits the Sun, and that needs to be equal to this gravitational pull by the Sun. As long as they're equal, then the Earth will be able to orbit the Sun. If it was stronger, it would get sucked in towards the Sun, and if it was lesser, Earth would start to float away. So, knowing that, this portion, ignoring the F equals for now, but just focusing on these other two parts, we can see that M2, this one would be also representing M2. These M2s on either side, so we can cancel them both out. And they both are divided by r, so we can cancel one of those out on each side if we imagine that we're multiplying both sides by r. And then we can square root both sides to end up with this equation, that velocity will be equal to the square root of the gravitational constant multiplied by the mass 1 over the radial distance. Substituting in now our gravitational constant as well as the mass of the sun and the radial distance, we have this. And so we can calculate that the velocity would be um, 29,847 meters per second, or approximately 107,000 kilometers per hour. Now, it's also interesting to note in this equation, v equals square root gm1 over r, that m2, the mass of the orbiting object, is not included here at all, which means it's not relevant to calculating velocity. So the velocity of an object orbiting a different object will only depend on the mass of the orbited object and its radius, or distance between the object orbiting and the object being orbited. Um, the mass of the object doing the orbiting actually doesn't affect anything at all. So even if you have, let's say, satellites orbiting Earth, you can have satellites of two different masses, but if they're at the same distance away from Earth, the same r, then they're going to orbit at the same velocity. So for practice work, we're going to look at page 296, numbers 1 to 5 and 11.